So hello, everyone, and welcome to our 8th lecture together. I feel like I've known you guys forever, but it's only been like 10 hours. Could you believe that? Anyways, this is our 8th lecture, September 23rd. And we are going to start by going over the quiz. So take out your quiz so you have it in front of you. Okay. And here we go. So the first question says, Nikki has a train set with 3 different engines. This is question 1. 3 engines. Am I sharing? Do you guys still see what I'm looking at? I don't think I'm sharing, am I?
Yeah, you're sharing.
You can see your iPad.
All right. So 3 engines and 8 passenger cars and 2 different cabooses. A, Nikki always makes trains by putting an engine first, a passenger car second, and a caboose third. How many different trains can Nikki make? Well, how many choices does Nikki have for the first car, for the first train, thing, whatever? How many options are there for,
3,
And how many options are there for the second stage?
8.
8. And how many options are there for the third stage?
2.
2. And then therefore, by the fundamental principle of counting,
48.
we multiply and we get 48 different trains. Agreed? Straight up fundamental principle of counting. B, Nikki's sister grabs 4 of the passenger cars and runs away with them.
Rude.
No, seriously, like crazy. Anyways, so there's 8 passenger cars and she takes 4 of them. How many different sets of passenger cars can she get? So essentially what we have here is she's taking 4 from 8. Does the order matter? Or does the order not matter?
Doesn't matter.
Does not matter. So that's what, 8C4 or 8C4 or 8-4. Either way, it's going to be 8 factorial over 4 factorial. 4 factorial, which is 8, 7, 6, 5, 4 down over 4 factorial, 4 down. Those cancel. 4 factorial is 4 times 3 times 2. The 4 and the 2 make 8. 6 over 3 makes 2. 7 times 2, 14 times 5. The answer is 70. So there are 70 different collections of 4 passenger cars that you can get. Does that make sense?
Yes.
Yes.
Unless I made a mistake somewhere. But I don't think
makes sense. I got 70.
you got 70. Okay, because the person whose quiz I happen to be looking at got 140. So I'm, I had to do a double take. Did I make a mistake there? But I don't think I did. And then we have part C. It says bonus, 5-point bonus. So if you didn't get this, don't worry about it. It's only a bonus. Suppose Nikki decides to make a train by putting 1 engine first, then 2 passenger cars, and then 1 caboose. How many different trains can Nikki make? Now, there's a slight ambiguity in this question, so I will accept either of the 2 different possible answers. The first one is assuming that his sister did not take 4 cars, and we're returning back to the original scenario. But I can see how someone could think that this is after his sister took 2 cars. So if that person or if anyone used that scenario, I will give full credit as well, because I can see it being ambiguous. So what's the possibility for the first number here for E?
3.
3. What's the first number for 8?
I put 16.
16 for what?
For the passenger cars.
Well, the first passenger car, how many options do they have?
8.
And the second one, how many options do they have?
8.
Not once the first one's being used.
Oh.
Can't use the first one twice.
Oh.
So how many options are there for the second one?
7.
7. And how many options for the caboose?
2 still?
Still 2, so 24 times 7, 140, 168 times 2, 336, is that correct?
That's what I got.
Okay, and
I don't know if that's
if-
correct.
hopefully it is. And if his sister took away 4 of them, this is not 8 and 7, it would be 4 and 3. And that would be 12, 24, 30, 12, 30, 72. So I will accept either 336 or 72. Does that make sense? Yes, no, maybe so?
Yeah, it does.
Okay, I mean, it was fairly representative of what we went over. No major surprises there, correct? Right?
So did you see my quiz that I sent you back?
I haven't graded them yet, but I did get.
Okay, you're gonna see, yeah, you're gonna see something on part A. I was very confused about that one. I gave you 2 answers for it. One of them is 48. I just wasn't sure if it was a 13 car set or a 3 car set. You'll see it, but is that like points off if I gave you an answer for another one? Basically, I answered it twice.
Yeah, so here's the general teaching philosophy on someone who does more than one answer for a question. It's like you're hedging your bets. Like, I don't know which one it is, I'll write both. And maybe the teacher will give me credit for seeing the right answer. But from a teaching perspective, we see something like that and we have to take off something, because then it's kind of like it's not fair, right? You're just listing like different possibilities and hoping one of them sticks, right? So I'll have to look at it to analyze it, but I would imagine I'd have to take off something.
Okay.
I hope that's reasonable and fair.
Yeah.
Which at the end of the day are both things that I try to, try to have when I'm grading. So, any other questions then? I mean, but does it make sense now that you've seen the answers? Maya?
Yeah, yeah, sort of. I mean, for A, I don't understand why it was just, you just multiply 3 of them if there is a 13 car set.
Because we don't use all 13 cars at any stage. Like when you first put your first car on the track, it has to be one of the 3 engines. The other 10 cars aren't there for this stage. It has to be one of the engines.
I see.
So there's
Okay.
only 3 options for the first car. And then once I've chosen that, the other 2, they're no longer with me because I'm not using them. Goodbye. They don't count. Now I
Okay.
have 8 passenger cars and one of those 8 has to be the next one. The 7 that I don't use, goodbye. And then the caboose, it's got to be one of these 2. So at no stage do I really have 13 options.
Okay, that's where I got confused. I thought you're using 13 of them. Okay,
Make
fine.
sense though?
Yeah, makes sense now.
Okay. Okay, any other questions before we move on?
Yeah, for the first one, I used kind of a tree diagram to help me visualize it. Just made it a little bit easier.
Never a bad idea to do that.
I only did like the first branch though.
Well, once
Just to see the multiplication rule kind of.
yeah, nothing wrong with that. I mean, I teaching my high school class today, I got 9th graders, the little shits. Anyways, oh, that was recorded. Great. Anyways, so like we're doing these basic algebra problems and I'm like, listen, I don't care what problem you're given. I don't care if it's advanced. I don't care if it's easy. If you have the option of having a picture, if you have the option of having a picture that could help visualize a situation, as a general rule, always use it. Okay, there's nothing wrong with that. In fact, one of the greatest physicists of the 20th century, anyone know their physics literature? Anyone know some great physicists of the 20th century? Give me at least one. Everyone should know at least one physicist. I mean, like, everyone knows this one. Anyone?
Einstein.
Einstein. Okay, great. So don't use him. Anyone know Newton was not in this century? Fig Newtons are this century, and those are almost as good. But no, Isaac Newton was in the 1700s, so that was a long time ago. You missed the century part, yes. So in this, I guess, last century, because he died in the 80s. Anyone ever heard of Richard Feynman? Richard Feynman? No. Anyways, he worked on the.
Oh yeah, I have in my English class. But I did read about him.
What would the English people want with Richard Feynman?
I don't know. It was
I don't
just
know.
that it's for educational, like liberal studies purpose. So that's why we have to know about everything. So, yeah.
Gotcha. Well, anyways, this guy, Richard Feynman, he actually won a Nobel Prize for introducing a kind of picture that can help solve some calculations. I mean, yes, he did other things as well. You don't get a Nobel Prize for one thing. He did other things as well. But the actual title, when he got the Nobel Prize, it was for contributions related to this thing called a Feynman diagram. So he actually won a Nobel Prize essentially for introducing a picture to solve problems. So pictures are extremely important and are recognized as being important, and you never want to miss them if you have the opportunity to do so. Anyways, that's just my comment on that. It's neither here nor there. But let's continue with where we left off. I believe last time, well, a couple of things. We had the second quiz, and I believe I said we're going to have another quiz tonight, right? Remind me of this. There was a quiz on chapter 4 that was supposed to be over the weekend, right? Am I delusional here, or am we all on the same page in that one?
Oh, yeah, that was mentioned in the recording.
Yeah. Okay. Oh, yeah. You can always go back to recordings. Hey, it's all recorded. Yes. Okay. So I will put that up today after the lecture, and you will have until Tuesday to do.
Professor,
Yes.
I actually had a quick question. I did see a little differently. I didn't get either of the answers. I just wanted to clarify to see like where I went wrong.
Okay. Who's talking?
Fritzy.
Okay. Go ahead.
Yeah, so I understood why we're multiplying like 3 times 2, but with the 2 passenger cars, what I did was I used the combinations. I used
Are we talking about A, B, or C right now?
I use combinations because you're choosing 2 passenger cars out of the 8, and you can choose any 2 of the 8. So I did combinations because order doesn't matter. You're simply choosing 2.
Okay.
And I ended up getting 28. So I multiplied 3 times 28 times 2, and I didn't get either or.
So you had 3 engine cars, 2 cabooses,
Mhm.
but when it came to the passengers,
Yeah, because you can choose 2 out of the 8, therefore
right?
the order doesn't matter. And
Why,
I did
wait. Why does the order not matter if passenger car 1 and passenger car 2 are reversed? Isn't that a different train set?
I thought it was just like if you're choosing like 2 random ones, it doesn't.
Right, but I'm asking you, if I'm creating a train
Mhm.
and I have, this is my passenger 1 and this is my passenger 2, and I reverse them, is that a different train set? Or a different train?
Yes.
Which means
I should have used permutation.
you could have used permutations. And if you would have done 8,
It would have been the same.
let's take a look. If you would have done, if you would have done, was it 2 from 8, correct? If you've done 8p2, which is 8 factorial over 6 factorial, it would be 8 times 7, which is the same that we had before.
Okay. All right. I see where my mistake is. Thank you.
But that's, that's in the grand scheme of, first of all, it was the bonus question. But even if it wasn't, in the grand scheme of things, you'd get the majority of points because you had the right idea. It was just a nuance that you had wrong.
Okay. All right. Thank you, Professor, for clarifying.
All right. Okay. That being said, I believe last time we finished chapter 5, right?
Yes.
Yeah.
We're on chapter 6.
Yeah. So we are on 6 now, moving right along. And chapter 6, the multiplication rule. Lovely. So let me unshare this here, and let me go ahead and share this here. Okay. Okay. So we got now the multiplication rule. So we have the addition rule. And that was about the probabilities for A or B, doing A plus B minus the overlap. And that, by the way, is chapter 4, which is the content of today's quiz. And now we have the multiplication rule. So let's see what it talks about. So we start with the example that we had in the last chapter of the princesses and the regular girls. And this isn't the original table. This is a table near the end that demonstrated independence, because 6/10 and 54/90 are both 60%. 4/10 and 36/90 are both 40%. Because we get the same thing for each row, these two variables, the crown or no crown and the princess or regular, are independent. Okay, so now it says, change the table. So we're making a new table now, so that each cell contains the proportion of all girls who fall into that cell. One cell has been done for you. We know there's 100 girls in total. 6 of them are princesses who wear crowns, so 6/100 or 0.06. So what would be the number that we would put into this one over here?
$54/100.
54/100, which if I write as a decimal is 0.54. And what would be over here?
4/100.
4/100, which as a decimal is 0.04. And what would be over here?
36/100.
Which as a decimal is 0.36. And then, of course, I can compute totals. 0.06 plus 0.04 is 0.1. 0.54 plus 0.36 is 0.9. 0.06 plus 0.54 is 0.6. And this one must be therefore be 0.4. Okay, so rather than having the counts, we have the percentages. 6 total, 6/100%. 4 total, 4/100, 54/100, 36/100, and so on. Okay. Don't know why we're doing this yet, but I could do it, correct? Nothing's wrong with what I did. We agree?
Yes.
Okay, so let's
Yeah.
try to see why we're doing this. So now suppose that you just had the marginal proportions. You just had these numbers here, 0.6, 0.4, 0.9, and 0.1. But you also knew, and this is important, you also knew that the variables are independent. Can I come up with a method that would allow me to fill in each of the four squares? Let's remind ourselves what they were. 0.54, 0.04, 0.36, right? So can I somehow, only with knowledge of the marginal values, the ones in the margin, and the fact that they're independent, can I somehow use that information to figure out this one, this one, this one, and this one? Does anyone see a way of doing that for this example, at least? Using these numbers to get these numbers. Anyone see a process? Does anyone not see a process? Just so I know if anyone's actually paying attention or not, because it's got to be one or the other.
I do not see a problem.
I do not see a process.
Just a guess.
Scroll down a little.
Can I what?
Never
Can I
mind.
just a guess?
Wait, hold on. Did someone ask me to do something?
No, I was
No.
asking if I can guess it, like just,
Yeah.
so would it be like 6 plus 4, and then it's like, that gives you the 1.00?
Well, I don't need these numbers. I already have these numbers.
Oh, okay.
I want these numbers. I want the missing numbers.
I can't see the, can you scroll down a little bit, please?
You mean,
Oh, okay, never mind. Every time my little thing pops up and it blocks the bottom half, but now I'm good.
now you're good. Okay.
I have, well, you can see that the 9 and the 6 makes 54 and the 9 and the 4 makes 36.
If I do what to those numbers?
Multiply.
So if I multiply 0.9 times 0.6, I get 0.54. And if I multiply 0.9 times 0.4, I get 0.36, which are what I want here. Does that also work for the other two numbers?
It does.
Magic. So 0.1 times 0.6 is 0.06 and 1 times 0.4 is 0.04. So this is it. Congratulations to whoever you were. I don't have names to voices yet, so I'm sorry. I can't give you the accolades and parade that you are due for coming up with the right answer, but that is exactly the right thing. If you multiply the numbers in the margins, that gives you the numbers in the appropriate square in the table. So 0.1 and 0.6 where they meet, 0.9 and 0.6 where they meet, 0.1 and 0.4 where they meet, 0.9 and 0.4 where they meet. This only works for independent variables though. Don't do this when they're not independent. It doesn't work that way. Okay, so this is the multiplication rule, which says if you multiply the numbers in the margins, that gives you the number in the table. Does that make sense? Just as a
So
as a
to
rule?
get the 0.06, what do you multiply?
You go to the margin beneath it and the margin to the right of it, and you multiply those two numbers.
Oh, okay.
And the same works for all of those numbers.
Wait, actually, Professor, can you scroll down? I'm not able to see the numbers beneath where you're multiplying.
You're not, what's the lowest thing you see? I'm just curious because
I just see crown. Like that's the only line I see.
interesting, because if I scroll up, my writing does not go with it. So someone also had that issue and said something was blocking it. Do you know how
What
you?
blocks it? Every time we talk, the bar of unmute or mute comes up, so it blocks completely that line.
I think you can drag that to the side of the screen. I have mine on the right side.
Yeah, that's what I was saying earlier.
Did
Yeah,
that,
if you-
How do you do that? Because yeah, that's the same issue.
you could hit view. I think you could even, standard is at the top and there's side by side speaker. Do you have that?
For
Should be
me,
at
I
the top,
don't. I only have.
Are you on a computer or is this?
No, I'm on a laptop or
Oh.
yeah, computer.
So then at the top right of the Zoom meeting, like right under where you'd close it, there's view, and you don't see that?
Professor, I have a question that's not
Yeah.
relevant since
yeah,
we're talking. For the quiz, it's quiz number 3 on what chapter? Chapter 4?
chapter 4. We did not have a quiz on chapter 2.
Right.
So it's the third quiz and it's on chapter 4.
Okay.
And you're giving it to us after class or it's already there?
Yeah, I might not put it up the second after class is over, but sometime in the few minutes after class is over, I'll put it up and you'll have till Thursday to do it. Till Tuesday to do it.
Okay.
Till next class. Okay.
You're also going to put up the chapter for homework solutions, right?
The chapter, yeah, I gotta do that too. So that, yeah, I'll do that today as well.
Okay.
Yeah.
Thank you.
Okay. So did you figure it out? So getting the thing out of the way?
No, because for me, view, the only thing that shows up is the show chat or the show manage.
Yeah, because the problem is that when I scroll up, it doesn't.
No, and even if you scroll up, I can't see the numbers that you're multiplying.
Right, that's what I'm saying. That's what I'm saying.
Yeah.
I can't do it.
I'm just gonna have to look at the recording.
Okay.
Try, is your thing in full screen mode or?
Yeah, it is.
Oh, okay, damn, sorry.
So I did the view and it worked for me. I was able to, when you click view, switch over to the side and it worked.
If you're in full screen, that might be why you can't see view. If you hit escape, it should minimize it.
No, it only shows show manage participants or show chat. That's on view. That's all it shows.
You can also
Oh, yeah. So you exit the full screen Zoom and then it's like on the top right of the Zoom meeting.
Yeah, if she says that she sees it, it doesn't
Yeah,
show.
it doesn't show for
speaker.
me. Yeah. Thank you guys. I think I'm just gonna have to look at the recording.
No problem.
Yeah, I'm sorry. Thank you guys.
Okay, so here is a frequency table for the boys. It has the same marginal totals as the table for the girls, 60, 40, 10, and 90. Those are the exact same numbers as it was for the girls. However, the proportions are not the same. So is 8 over 10 equal to 52 over 90? Is 8 over 10 equal to 52 over 90?
No.
No, which means these variables are not what?
Independent.
They're not independent. Well, let's see what happens when we try to use the multiplication rule. First, what percent of boys fall into this upper left category?
0.08.
0.08. And I would try to scroll up to make sure you can see it, but I want to have these numbers here as well. So that's really the best I can do. Hopefully you can see that. But in this one is 0.08. And how about directly beneath it?
0.02.
0.02. And how about to the right of 0.08?
0.52.
0.52. And how about directly beneath it?
0.38.
0.38. And let's fill in the margins. The top right margin is what?
0.60.
0.6. And directly beneath it?
0.4.
0.4. And directly beneath that?
0.1.
Well, not 0.1, but 1.
1.
Right? And what over here?
0.90.
0.9. That's a horrible point, but hopefully you get it. And what's the one over here?
0.1.
0.1. So if I multiply the 0.1, for example, times the 0.6, do I get the 0.08?
No.
No. So this does not work when they are not independent. It's only valid when they are.
So it like independence and dependent, that doesn't have anything to do with like the mutually exclusive stuff, right?
No. Well, it does, but only in a slightly deeper way, because if two events are mutually exclusive, that means you can't be in both at the same time, right?
Right.
Which means if you're in one, you can't be in the other. And therefore, there's some kind of connection going on if whenever you're in one, you can't be in the other. So if two events are mutually exclusive, they can't be independent.
Yeah, so they would not be independent.
Right. But the math for that, we're not going to worry about that. It's just more of a conceptual thing.
All right. So for the sake of these, it's independent or not independent.
Correct. Now, if they were independent, what number would go here?
0.06.
0.06. And what number would go to the right of that?
0.54.
0.54 and 0.36 and 0.04. Okay, does that make sense?
No.
It does not?
No, I don't. I'm kind of confused now.
Well, if they were independent, then when I multiply 0.9 times 0.6, I'd have to get 0.54.
You said divide?
If they were, this is what I would have to get, right? This particular table is what numbers would have to be there for them to be independent.
But then the second table is wrong, right? Because
the second table, yeah, the first table and the second table do not agree. And the reason is because I look at the actual numbers, it's not independent. This would only be true if it were independent.
Oh, okay.
This is if it were independent, but it's not. This is not correct. If it were independent, these would have to be the numbers. But they're not those numbers. The numbers were, I don't remember what they were, but whatever they were different numbers, which means it's not independent. That's all this is trying to demonstrate. Does that make sense?
Yes, thank you.
Okay. And this is the rule in encapsulated form. If A and B are independent, then the probability of A and B occurring is the product of their individual probabilities. In other words, the probability of being in any given cell, any box, is equal to the number beneath it times the number to the right of it. Those marginal probabilities, those are these, P of A and P of B. If they're independent, I can multiply them together to get A and B, which is the box. Okay, so if I go back up here, I would say if A is being a regular boy and B is having a horse, then the probability of A times the probability of B would give me the probability of A and B. In other words, 0.54. But it's only valid if they are independent. If they're not independent, you cannot use this rule.
Would we only be able to know that it's independent by trying to do the multiplication tricks with the table, or?
Well, if you're given the table, you can certainly confirm whether or not it's independent. Right? I can multiply, hey, I get that. Multiply, hey, I get that. Oh, I get it. Hey, they're independent.
Okay.
If you have the table, you can certainly confirm independence.
Like on a quiz problem, will it say such and such, whatever, independent, or will it kind of be up to us to figure it out? Or I guess it could go either way.
You go either way. I mean, I can promise you this. Whatever I give you is enough to solve the problem.
Yeah.
But I can't promise it's going to be one form or the other. And like the last example, I can't promise that I might not look at it after the fact and say, oh, that wording was a little vague. That's always a possibility. You know, sometimes students who are learning something see nuances in the words that as a teacher we don't think of, because we have something in mind.
You see it already and it.
That's just, so that's why you have people who edit and people who proofread and stuff like that. They're the ones who're supposed to come along and say, hey, what do you mean by this? What do you mean by this? And so on. When I write tests, I don't have that. So sometimes I don't see it always like you might see it. Okay. So this is the rule. This is the rule. So we don't have to do this because we did it already, but let's go to area models. So area models, such as the one shown in the next example, are often used to help elementary and middle school students visualize the multiplication rule for independent events. Example, 3 out of 5 people sing in the shower. You want to find the probability that both your favorite actor and the CSUN president sing in the shower. Intuitively, would you expect your favorite actor singing in the shower and the CSUN president singing in the shower to be independent, or is there some kind of connection going on between them?
I think they're independent.
Well, do you intuitively feel that one of them should have any effect on the other? No. So then they would probably be independent. Unless it just so happens that the CSUN president's, family member is your favorite actor, or some weird, situation where they grew up together and they might have the same inclinations or something like that. Chances are they're not going to have anything to do with each other. So here is a area model, like we did before with the tree diagram situation. Your favorite actor, it says 3 out of 5 people sing. So I could make 5 rows, sings, and doesn't sing. And the CSUN president, same thing. 3 out of 5 people sing. So I make 5 columns, sing, doesn't sing. And we're looking for the probability that both of them sing, that both sing. So which boxes would count in this model for both of them singing? Which of these boxes would count?
The first one?
Just this one? Is there any other that would follow? Huh?
The second one, the third one.
Okay, any others?
And also the other one under that one, the 3.
Anything else?
And then under that, another 3.
So how many ways in this area model, how many different situations would we have both of them sing? And how many different possibilities are there altogether? Equally likely possibilities. What does the area model tell us?
9 out of 25.
9 out of 25. But if we go back to the original 2, which is 3 out of 5 and 3 out of 5, what happens if I multiply 3 out of 5 times 3 out of 5?
You get 9 out of 25.
I get 9 out of 25, which means that this area model has successfully represented the rule by showing that this times this does in fact give what I expect based upon areas. This is one way of demonstrating to a young person, middle school, high school, etc., the rule that we're talking about. Does that make sense? Yes, no, maybe so.
Yes.
Yes.
Yeah.
Okay. Okay, we did that already. Okay, so here's another one. It says 70% of 18 to 34-year-olds shower for longer than 10 minutes, while only about 30% of people aged 55 and older shower for that long. Suppose you pick an 18 to 34-year-old at random and a 55-plus-year-old at random. And we want to find the probability that both shower for longer than 10 minutes. It says draw an area model and shade in the area that shows an event that both the 18 to 34-year-old and the 55-plus-year-old take showers that are longer than 10 minutes. Then use the area model to find the probability that both shower for longer than 10 minutes. So how would I do this with an area model? Anyone?
I'm trying to process the problem.
That's fine. Take your time. Processing is good. I processed once.
Wouldn't it be that there should be like a category? So like, let's say like the x-axis for the table is the 18 to 34-year-olds. So they're
So what are your two axes? Hold on. What am I doing here? Well, actually, you know what? I can do this. Okay. So what were you saying again?
that one side is, so it's like, say the x side is 18 to 34-year-olds.
Okay, that's my 18 to 34-year-old. And this,
Yeah,
this is my 55 plus. Okay. Now what?
And then wouldn't it be a category where it says shower longer, and the other would be
Doesn't shower longer.
One
I'm listening, I promise.
it would be like long shower and a short shower category, and like both sides.
Okay, but the question is how much room should each one take up? That's the key.
Oh.
The key is how much room they take up. So showering longer is 30%. So something like this, where this is 30%, 0.3, and this is 0.7. Oh, crap. Something like this. And then, of course, these lines should go to the end. So I have 30% represents the shower longer than 10 minutes, and 70% is not. And then I do the same thing. Then I do the same thing here. 30% is how do I hold on a second. And then I'll shade in. So that would represent the ones that represent both the 18 to 34-year-old taking longer than 10 minutes and the 55-plus-year-old taking longer than 10 minutes. And how many boxes are there altogether in this diagram?
100.
100.
10.
Then out of those 100, how many of them represent both the 18 to 34-year-old and the 55-plus-year-old taking longer than 10 minutes?
9 boxes.
Which, by the way, is equal to 3/10, which is the first one, times 3/10, which is the second one. So the area model just again demonstrates the mathematical relationship, but in a visual way.
I'm just a little confused. I noticed that you did a 30% box, but it says 70% of the 18 to 34-year-old shower longer than 10 minutes. The first sentence in the question.
Oh, crap. Okay, so then it should go like that.
And then the only place that they overlap is those 9.
Well, just not 9 anymore. Now
Oh,
it's
okay.
now it's 27. Now it's 21. So is that better?
Yeah, okay. I get it now. I
Yeah.
thought I was misunderstanding something.
No, I'm just really tired, so I'm sorry. You all want to be teachers one day, right? This is a
Planning on it.
So,
Yep.
I should probably stop recording for a second when I say this, but look for other options because it's a really tiring job. I'm really tired all the time. Anyway.
You teach a lot, Professor.
But you also teach a lot, yeah.
Yeah, I know. But that's the thing. If you want to make a halfway decent living, you can't just have one teaching job. It's should marry rich. That's what you should do. I'm still working on it, but or win the lottery, one or the other. That.
Let's see which one comes first.
Oh, that someone said something. What? How what? Someone say something before which one will come first? Yeah, I don't know. The way I'm going, I'm not even sure either of them will ever come, but that's beside the point.
Oh, I was just saying that I'm working on the lottery.
Working on the lottery, good choice. That's my recommendation. And if anyone here wins, we should make a pact. If anyone here wins, you should give me like at least 10%. That's the max. I'm not giving you anything, but if you guys win, you should give me 10%.
I'm not giving you
Give us
anything.
good recommendation letters.
What's the statistical probability if we buy 10 tickets every
That's
week?
not fair, but if you win, you have to give us 10% too.
But I have to give everyone 10%, or I break up the 10% into 32 pieces and give each one a little bit.
Okay, that's still fair too, but
Fine, deal. All right, deal. I accept that.
I mean, it's something.
It's something. Hey, anything's better than nothing, right? All right, so we did that. Okay, here's another one. It says, show how to use the multiplication rule for independent events to compute the following probabilities. You spin the spinner twice. What is the probability that it lands on yellow both times? So first, we're going to ignore the fact that it says green when it's really blue. We're going to pretend that that's not happening, unless I'm colorblind. Anyone there see green there, or is that blue?
That's
Blue.
definitely blue.
I see
It's
blue.
green, but it's like an aqua green type
I was
of
thinking
blue.
that, like
That's-
aquamarine, right?
Yeah.
Isn't it like what's a fancy word for like the color blue? It's like one of those weird colors.
Turquoise.
Azure.
Boy, teal, that's what I was thinking of. But turquoise,
Cyan.
Oh.
that stuff works too. What do you say? Which one?
Cyan?
What the hell is that? Is that a thing?
So, yeah, it's one of the ones that goes into a printer. Cyan. CYAN.
Yeah, I've heard
It's
of
really
that.
close to the color.
Oh yeah.
I was thinking of teal though, but yeah, cyan. I've heard of that. I've heard of that. Yeah, I remember once, this is like a few years back, my nephew was like turning 4. He had a birthday party. And I go across town and I get there and he was so excited. He made place cards of different colors, blue and red and green and yellow. And he's holding them as I walk in the door. And he goes, Uncle Dave, he goes, what's your favorite color? And I go, chartreuse, which wasn't one of the colors. So he started crying.
No.
Good time.
Poor guy.
Good time.
But you tried so hard. It's just like
No.
how like
I don't even know what chartreuse is, but I just thought it was funny. Anyways.
no.
Yeah. Oh, good times. I got to get my pleasure when I can, guys. What can I do? Anyways, so back in this example.
Fair point.
What's the probability that he lands on yellow both times? So first, ask yourself, are the 2 spins independent? Does whatever happened on the first one matter when it comes to the second one? That's the first question you ask. Now you might say, well, you might say yes. You might say, well, wherever I flick it from, depending on where it is, it's going to influence where it lands. But you can't really quantify that because the amount that you flick is not the same every time, right? It's a random strength. So we're going to go into the assumption that they're independent. Is that what you were going to say or say something else? I overrode you. I'm sorry.
I was going to say it's independent.
Yeah, they're independent. So then the probability of landing yellow the first time is what?
1 out of 6.
1 out of 6. Now you might think it's 1 out of 4 because there's only 4 possibilities, but remember they're not equally likely. Dark blue versus cyan or teal or whatever that is more likely to occur than the rest. So what we need to do if we want to use basic probability is we have to divide it into equally likely outcomes. It just so happens that dark blue is 3 of those outcomes, but nevertheless, here you can easily see that yellow is 1/6. And the second one is independent. That's also 1/6. And as a result, what is the likelihood of both of them being yellow?
1 out of 36.
1 out of 36. And what about red the first time and blue, or at least dark blue, the second time? What would the probability be there? Or at least what would I multiply to get the right answer?
1 over 6 and 1 over 2.
1 over 6 times either 1 over 2, or if I don't simplify and keep it with the same denominator, 3 out of 6, but it's the same thing. So the answer would be 1 out of 12. Does that make sense? Any questions on that? Comments, similes, metaphors?
Wait, so
Yeah.
so the 1 over 6, why did you multiply it twice?
The first spin and the second spin,
Oh, okay.
right? Each spin is one
Like
of
they're 2 different colors.
which one's 2 different colors? It's yellow both times.
Oh,
First one, 1 out of
okay.
6, and the second one is 1 out of 6. They're both yellow, right?
Okay, so you just combine. Okay, got it.
Yeah, and it says use a area model, but I'm too tired. So let's do this one.
Like when we were using the dice, right? Like
Yeah,
the double.
essentially, exactly. It's getting double 6s. You flip a coin and then you roll a die. What is the probability that you get a head and a 6? So first ask yourself, as always, are these independent? Does what I get when I flip the coin have any connection to what I get when I roll the die.
No.
Then they're independent. In which case, if I just focus on the flipping the coin, what is the probability that I get heads?
1/2.
1/2.
1/2. And if I roll the die, what's the likelihood that I get a 6?
1/6.
1/6. So the final probability of getting both of them occurred is 1 out of 12. And I can go one step further. Okay, it can be more than 2 events. It can be a sequence of events. Suppose I flip a coin and I roll a die and then roll 2 dice. So I flip a coin, I roll a die, and then I roll 2 dice. So what is the likelihood that you get heads, a 6, and then a 5, a sum of 5? So first, do we agree, ask yourself, are these 3 independent events? My first flip, my first roll, my second roll, do they have anything to do with each other? Does one affect the other in any way?
No.
No, fine. Then what's the likelihood of getting heads on the first, on the flip of the coin?
50/50.
1/2.
1/2.
1/2, sorry.
It's okay. And then getting a 6 if I roll 1 die,
1 out of 6.
and then getting a sum of 5 if I roll 2 dice.
Want to be
4 out of
1
36.
of the 12?
It's well, there's 36 outcomes, right? And there's 4 ways of getting a 5. Do we agree with that? 1, 4, 2, 3, 3, 2, 4, 1.
Mhm.
So 4 to 36, which becomes 1 out of 9. And then we get what, 1 out of 108. Something like that, right?
Mhm.
Okay, what about if I flip a coin 4 times? What's the likelihood that all 4 are heads?
One four.
Not 1/4.
No, wouldn't it be 2/4? But then it's still 1/2.
2/4 is 1/2, but that doesn't make sense, does it?
No.
So what's the probability that the first one's a head?
1/2.
And the second one?
1/2.
And the third one?
And then 1/2.
And the fourth one?
1/2.
And then what do I do to those numbers?
Multiply.
Multiply. I don't multiply by 4. I multiply them all together. 1/2 times 1/2 times 1/2 times 1/2. Which gives me what?
1/8.
What? No, not 1/8.
No, it's 16.
1 out of
So Liliana got it first. She wins. We'll throw a parade in her honor next time. 1 out of 16. Does that make sense?
Yeah.
Yes, okay, all right. All right, how much money we got? I'm so tired, I want to go home. All right, so let's see what we have. 57% of California. Huh? I can't, I'm teaching for the next 9 hours, so I can't. All right, literally, my last appointment's 11 to 12 tonight. Yeah, exactly. All right, 57% of California students speak English at home. If you select 5 Californian students independently at random, what is the probability that they all speak English at home? Yes, we're almost done here. I know. Every time I knock one off, it's like, okay, one less to go. Not that I want to knock you guys off. That would be kind of weird, but hopefully you understand what I'm saying. Anyways, what's the probability that if you look at 5 California students independently, that they all speak English at home? What would that be? How would I compute that? It's no different than the previous problems. It's just you can't get a nice answer without a calculator, but I can still write it down. What would the expression be that I'm looking for? Anyone?
I have a question.
Yeah.
Does 57% have anything to do with it?
Yeah, I would hope so.
Okay.
Otherwise, I would think, why would they give that to me? So yeah, chances are it matters.
Would you do it out of 100, the 57 over 100?
You could, if you want to write it as a fraction, nothing wrong with that. But still, I need to know what it is.
57 over 100. And do we multiply it over 1/5 or that's the part that I'm struggling with.
That's the key. That's the key. I mean, do what we've done this entire day, which is when you have a sequence of independent events, you compute their individual probabilities and do what with those numbers?
Multiply.
Multiply them. So what is the likelihood that the first person speaks English? Right? You're picking 5 at random. So I pick someone and I look at that person that I picked and I'm thinking to myself, what's the likelihood that this person speaks English?
Okay, so we do 43 over 100
Well,
multiplied.
hold on.
Because it's 57% of California students speak English at home, and we're looking at the probability that none speak English at home.
No. That's the second part.
Okay. So then we're just doing the first one.
Yeah, we'll
So
do-
if it's the first one, so it's 57 over 100 multiplied by 57 over 100 five times.
Okay, so
Or you could just
5/7 to the 5th power, done. All right, 0.57 is the first one, 0.57 is the second, 0.57 is the third, 0.57 is the fourth, 0.57 is the fifth. Multiply them all together. It's the same thing as raising to the 5th power. Take out your handy dandy calculator. And you get what number? Anyone have a calculator?
6%?
Yeah.
About 6%. Now, what's the probability that none of them speak English?
0.43 raised to the 5th.
0.43 to the 5th, which is? Anyone?
Like 1.5%?
Yeah, about 1.47%. But again, it's the same rule. Independent events, you look at each probability and you multiply them all together. In the first case, all of them want to speak English, or we want all of them to speak English. It's 0.57, 0.57, 0.57, 0.57, 0.57. None of them speak English, 0.43, 0.43, 0.43, 0.43, 0.43. If I said that 3 of them speak English, that's a whole other problem. That requires a little more sophisticated stuff than we're going to worry about. Okay, so what we're doing is just the extremes, all of them or none of them. Does that make sense so far?
Yes.
Everyone? Okay.
Yeah.
Often it's a judgment call as to whether events are independent. And so whether you can use the multiplication rule for independent events. Ooh, group activity, you be the judge. A driver was cited for overtime parking in a 1-hour zone. Been there, done that. The parking officer had come by and recorded the valve stems on the left side tires were at 1 and 6. When he came back over an hour later, they were still at 1 and 6. The driver claimed he left and returned. Now, if you leave and return, your wheels are going to rotate a lot. Is it likely that it rotates to the point where the stems are basically in the exact same spot that they were before?
No.
So would you rule guilty or not guilty?
Not guilty.
Guilty. No,
Wait,
guilty.
guilty.
The logic there is a little confusing. So if it's unlikely that the person actually left, they're probably lying, I would rule guilty, right? Of course, is it possible that they're not lying? Is it possible that they came back?
Yeah, it's possible, but it's rare.
Yeah, it's possible, but it's unlikely to the point that the police officer would probably be justified in giving the tickets. And if you came to court and said, I left and came back, the judge would probably say, we don't believe you. Not that that's not true. It's not that it's impossible. It's just that we don't believe you. So the question now becomes, what if events are not, oh, so close to it. What if events are not independent? So without looking, you pick a ball from a box that contains 5 red balls, 3 yellow balls, and 2 blue balls. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is the probability that both balls are red if you replace the first ball before drawing the second? What is the likelihood that both balls are red if you replace the first ball before drawing the second? So if you replace the first one, would they be independent?
Yes.
Yes. So what's the likelihood that both of them are red? What's the likelihood the first one's red?
5
3
out
out
of
of
10.
10.
And how about the second one?
And it goes to 9. So
No, you replace it.
Oh, okay. Sorry. 5 out of 10.
You replace it. We're back to where we started, correct?
Mm-hmm.
Now, what if I do not replace them? What's the likelihood that both balls are red now?
5 out of 10 multiplied by 4 out of 9.
Yes, 5 out of 10, 5 red, 10 total. 4 out of 9, 4 red, 9 total. So they're not independent because the first one affects the second one. If the first one is red or not red, it affects the likelihood of the second one being red or not red. Does that make sense?
Yeah.
Well, these are not independent. And if they're not independent, we have a slightly different rule. And this is more general. This one holds independent or not. So in the independent case, we multiplied them. In this case, we also multiply them. But what are we multiplying? We're multiplying the first events by the second event, given that the first one occurred. So in the last example, the first one was 5 out of 10. And then given that it occurred, the second one was 4 to 9. So it's the same multiplication. It's just the numbers change a little bit. So suppose you draw 2 cards from a deck. What's the likelihood that the first is an ace and the second is a jack if you replace? So first, what's the probability on your first pick that it's an ace?
Four out of 52.
4 out of 52. And if you replace that, what's the likelihood that you get a jack on the second one?
Also 4 out of 52.
Also 4 out of 52. But what if you do not replace it? The first one's still 4 out of 52. But now what's the likelihood you get a jack on the second one?
4 out of 51.
4 out of 51 because there's one fewer card in the deck, but there's still 4 jacks. Does that make sense? So again, same rule, you multiply, just be careful. Things change after the first one. So your second fraction will usually be different than your first fraction. Make sense? I hope.
Yes.
I hope. Okay, so we did good. We finished chapter 6 today, which means chapter 6 homework is due sometime, right? So, yeah, so today I have to teach a class now for the next hour, 15 minutes from 2 to 3:15. No, it's 3:15 now, from 3:10 to 4. And then I have my statistics class, my next one from 4 to 5:30. But at 5:30, I will put up your quiz. So expect it to be like around 5:45, unless I fall asleep or die. One of them is certainly possible. All right, are there any questions with what we did today?
We wish you the best.
Oh, well, thank you. If I have the best, can you have the second best?
Yeah.
Because you can't also have the best if I have the best, right? That doesn't make any sense, right? I
The
don't know.
best can be divided in any way, shape, or form you like.
Okay, I'll take it all then. Okay, my class started 2 minutes ago. I gotta run, but I will see you all
Thanks, Professor.
Tuesday. Have a good.
Thank
Should
you,
I-
man.
Thank
You're
you.
you're posting the quiz.
Bye,
in-
good luck.
Next Tuesday?
Good luck.
Yeah, thank you. The quiz is due Tuesday.
Okay, perfect.
Okay?
Have a great weekend. Take care.
Okay, bye.
Bye.
Okay. Oh, and Catalina's here. Okay. Catalina, I'm gonna ask you if it's okay. I'm gonna stop recording first, but I'm gonna